another presentation of mine. I'm going to talk about optimal design of GNSS interference localization, wireless net security network. And before I start, let me give you some introduction about from where this idea comes and what is its importance. And we all know that one of the methods for tackling the climate is smart cities. Smart cities is a city or a small city is a city. There are cities with full of sensors and networks, wireless networks inside. These sensors can be active, can be passive, can be camera or any other. So when we have this city with full of sensors for navigation, for communication between different devices, the cybersecurity, which is related to mainly the handling the data, and also the signal security, which transmit information between the sensors, will be very important. Jamming and spoofing are two known signal interferences. Jamming means to transmit a signal close to the frequency signal as the same band to somehow not to let the receivers or the other sensor receive this signal, or it is called a signal is jammed. And spoofing is that they send a similar signal to the transmitter signal, but the signal is fake. So in that way, by spoofing, you can get control of different, for example, vehicles by just sending a fake information so that these autonomous vehicles move to the direction that you want. So these are two known interferences that have higher risk of occurrence in the smart cities in the near future. Examples. Yeah, so it was a TV amplifier. Was jamming the GPS signal operation at the harbor. Also, a small jam, not for the delivery, but disrupted the ground-based augmentation system, aiding the aircraft approaches to Newark Airport while driving the nearby highway in 2009. So, also, the Central Radio Management of South Korea reported several disruptions for the GPS jammers, or also the similar things in Italy. As you will see, this simple jammer, they are rather cheap, can cause huge problems in the navigation signals, especially when they are equipped with navigators. And when the smart cities, the smart cities and autonomous vehicles, which will be more and more dependent on this navigation, or navigation by sensor, navigation by GNSS, or any other thing. So the interference can cause huge problems and risks, even in people's life. Here I explain what's the difference between the geodetic network and localization wireless network. In principle, they are similar. You have some known points, and you have unknown points. And between these known points and unknown points, you have some measurements. And from these measurements, you try to estimate the error of the unknown points to estimate the error of estimate the position of the unknown points. This is completely similar, like geodetic network, for example, resection and intersection that we do normally in geodesy. But for optimization, there is a big difference. In optimization of geodetic network, the unknown points are moving in such a way that the error ellipse or some criteria related to the quality of this coordinates of the unknown points are matched or are fulfilled. However, for wireless level, these are the noun points should move and to get an optimal configuration in such a way that they cover the whole area of study with better accuracy. It means that if we have some interference device, the probability of determining its location is much higher when we change the position of the anchor nodes or the base points. A localization wireless security device is a collection of anchor nodes having coordinates and control nodes that they can be representatives of unknown point or interference device. The distance between control points is considered as resolution. A configuration that we talk is the geometric shape created between these anchor nodes. So the main problem here, if we want to cover an area which is already covered by control nodes, what configuration the anchor nodes should have so that they can determine the coordinate of this control node with high quality. That's the main point of optimization of a localization wireless security network. The observables are very similar to the distance measurements and the azimuths on north and distance difference, but we call it the time of arrival. What does that mean? It means that when the signal arrives to the receiver and we will record that time, this time is there is the time of arrival of interference, and this time of arrival has a direct relation with the distance. So if we have the velocity of the signal, which we have by the time of arrival, we can estimate or determine the distance. And distance is a function of coordinates between the transmitter and the receiver. So we can have this mathematical model. Angle of arrival, if we have an array of antenna, so that they can determine from which direction the transmitter, the signal, interference signal is coming, then we can have a Buring equation for that, as you see in equation 1b. And as you see, this equation is also a function of coordinates of the transmitter and receiver. And time of difference of arrival is actually the time of difference between the signal which reaches to one station and from the same transmitter to another station. If these stations are at the same or have the same or they are co-located at each other, then this time difference will be zero. Therefore, this time difference code is due to the that these points are not co-located, are not at the same place. And based on that, we can have a time difference of arrival when we have the velocity of the signal. And also, as you see, this time of difference of arrival, time difference of arrival is function of the coordinates of the transmitter and two known coordinates of the anchor nodes. Localization is the same process as we do in intersection or resection or geodetic networks. We have to linearize or mathematical models, create a Gauss Markov model or system of equations, and solve it by a least squares process. So the equation 2b you see here is the solution of the linearized system of equation. And the variance covariance matrix of the estimated parameters or unknown coordinates, as you see are in equation 2c. So for optimization, my focus will be on this variance-covariance matrix. Okay. If I have this variance-covariance matrix as observables, and I expand it by a Taylor series. So based on the initial position, I can have an initial variance-covariance matrix plus some updates to the coordinates and on the right side, and also the derivative of the coordinates with respect to the coordinates of the coordinates, which are actually showing the sensitivity of the variance-covariance matrix along each one of the coordinates of the anchor nodes. So based on this Taylor expansion, in this example, as you see 4 points, then we have at least 8 observations in this example, 8 unknowns. And the variance-covariance matrix that we have for 1 point contains 4 elements. So we have 4 equations, but 8 unknowns. It's not solvable. Therefore, we have to consider more points, but for the same anchor nodes. So after a while, we add more and more control points. The number of observations or number of the elements of the variance-covariance matrix of the unknown parameters will be much higher than 8, the total number of the coordinates or unknown parameters. Then we can create another Gauss Markov model, as you see in equation 4a, and solve it by a least square. But the problem is that when you use least square, there is a high risk of lack of convergence in the conditioning. And also anchor nodes, when you estimate them, they go very far from the area that you want to study, or sometimes they come at the center of the area, and sometimes they become collinear. So it's very not which is unstable. To solve this problem, we need to limit the search area for the coordinates of each anchor node. So for example, in equation 5a and 5b, you see that each anchor node has x and y coordinate, and they should be between 2 values. For example, x coordinates should be moved from the initial value 400 to the left or 400 to the right, something like that. And we can write it in matrix form in equation 5c. Or we can add another constant here. For example, I present a directional constraint, but you can have any other constraint. For a directional constraint, you want the points to move toward a specific direction. That's all. So, and when we have this optimization model, we have to subject this optimization model that this is hopefully without constraint, it will be an ordinary least squares problem. But we have to subject it as a least square problem. It does not give us the solution that we want. We have to limit the search area, and also, if necessary, we can add then any extra constraint that which we think that it could be useful for an optimization. For example, you get this map, figure 2, which is the photo of the Landvetter airport of Sweden in Gothenburg. Point M, O, and N are selected as initial points. And you see how the coordinates frame is defined. And this squares that you see around each point is a search area, which is 400 by 400 to the left, 400 to the right. So it means that I have an initial value, and I just want that optimize this network, the points, only in such a way that this point moves inside these squares. What you see here is an initial dilution of precision, is the is actually the trace of the variance covariance matrix, the estimated variance covariance, is showing the geometry, effect of the geometry on the quality of the estimated coordinate for the control points. And as you see here, it reaches to 6, value of 6. But if I optimize them just based on the constraint that I show you before, limiting constraint, then this maximum value will reduce down to 4. And as you see, it has better coverage over the area. In this case, in both cases, as you see here, I use time of arrival as observable. So if I use angle of arrival, the situation will be the same. In the initial variance covariance model or initial DOP, I would say a trace, square root of the trace, you see the maximum reaches to 6, and after optimization to 4. So, but the time difference of arrival didn't work for that network because it's based on the special geometry of that. This is too, for example, this triangle which you see here with the corner at point N is too narrow. So this is a little bit, the geometry is not very stable and very, very good geometry. And for time difference of arrival, it doesn't work. It works much better if the area is square. So here, to show that, I use Arlanda Airport of Sweden again. You see the coordinate frame defined and the area, the initial points, and the area, that's the search area for each point that's moved. If I use this design and estimate the DOP, I will get this, and you will see that in some areas this maximum reaches to around 9, especially at point P. Now, based on those areas that I show you for the limiting the coordinate variations, I get much better result. The maximum value reduces down to 4. But what is a problem here? We do not have that much control over the movement of the point. For example, point P will be placed in the forest amongst trees, which is not a good point. And some points like N is the middle of this road. And there's not also always close to road. That's not a good place and very safe. Then we selected the directional constraint so that the points move along the runways of the airports, so they are safe operated. If even if we have interference due to the aircraft movements around, and we know that they are due to the interferences are due to the aircraft. We know that it's nothing from outside. So as you see, this method works well, and the optimization based on the time difference of arrival for Arlanda Airport. So it's very important that always have the research area. We have some constraints. It's based on the geometry of the area. You look at the geometry based on that design, see which type of constraint. And also it's very important that the initial places for the design or initial design plays a significant role in the design. These are the references that I have used, and thank you very much for your attention.